I look the same as I did yesterday.
Yeah, no problem. Oh, here we go. Here's Shandian. All right, so I'm recording. Shandian, are you there and can hear us and everything?
Yeah. I just try to unmute myself.
Okay, great, thanks. Okay, so I'm gonna kind of get started here really quickly. So the way that this normally works is, the mic's over here, is that student will defend and present, and then we'll open it up afterwards for questions from the general audience, and then questions from the committee. However, today we have a very sharp 1 o'clock. We have to be out of here deadline because there's another thesis right after this one. So we're going to be pretty close on time. So since all of the general audience members are people in Jacob's group, just please ask him questions later, okay, just to help us save time. And then that way it gives the committee more time to really grill him good. Yeah, so with that, don't ask me, please just hold the questions to the end is the way we'll do it. And then we'll switch directly to committee questions just to make sure we get those out of the way. And so, yeah, without anything else in the way, Jacob, please go ahead and take it away.
Okay. I'm trying to get something to disappear from the screen here when I present. Let's see if it's going.
There it is.
I don't know how to get rid of that.
Just say got it.
It's not showing up on my screen. It's a problem.
Oh,
On my
just say,
laptop screen.
oh, then just
Well,
click
it's
it.
on the extent, yeah, just click down.
Look at TV. Move your mouse. There you go. Move it to got it.
Oh, behind it.
Oh.
Oh, it's on your mirror.
Yeah,
Can you
it's
just
just
hit
weird.
What if you stop share, hit got it and share again?
Yeah.
Let me try that. Hopefully.
It's always got to be something weird at the beginning, right?
Yeah.
There we go. Okay, here we go.
Sorry for the delay, everyone online. So first off, I'd like to thank everyone for coming here today, taking the time to listen. I hope you're all able to take something away from the talk I'm about to give today. So I'm Jacob Zamora. I'll be presenting on machine learning for the development of microstructure sensitive damage models and engineering applications. So I'll start off with the motivation of the project. So as engineers, we're very familiar with material modeling. So by modeling, we're able to reduce the need for costly experiments, as well as material modeling assists during the design phase. So there are a lot of uses for it. The goal of material modeling is to predict material response to external stimuli such as forces. So what I'm showing here is a very common example of a stress strain curve for ductile metals. Just a uniaxial curve, stress strain. I've labeled the elastic region, which can be modeled using Hooke's law. I've also labeled the plastic region. You can identify initial yield using a number of yield criterion. So a common one is von Mises yield criterion. Also involved in the plastic region. Okay, there we go. Sorry, that was just looking at you weird. So also involved in the plastic region for a plasticity model that typically involves 3 components. You have a yield criterion, a flow rule, and then a hardening rule as well. So those 3 components usually make up plasticity models. So as we know, these are conventionally developed using analytical approaches. You can use experimental data and fit equations to the data, or use underlying physics in the development. So for von Mises, as a physical interpretation of the elastic strain, energy of dissipation, reaching some maximum critical value. So from these classical approaches that I've shown, there are modern analytical approaches that have increased accuracy. So a lot of the very old ones, they had a lot of assumptions underneath them. So they're not very accurate, but they're still very useful for engineers. So specifically for these modern analytical models, they have a number of advantages. They're interpretable. This is due to their closed form analytical expression, as well as they're compliant with software. So for example, finite element software, structural analysis software, analytical models are compliant with those. But they do have a number of disadvantages. Limited flexibility. So modern analytical models, they're usually very specific to materials or loading conditions. Also, slow development time. Takes a certain amount of time to develop these models just because you have to go through the rigorous steps of the physics and everything behind it. Also, there's often calibration demands for these modern analytical models. So this is this takes a lot of time, and you commonly use experimental data to do so. So alternatively, this work, we're looking to leverage modern computational capabilities to rapidly generate accurate material models. So what is data-driven modeling? So we're seeking to find and apply relationships in data to make predictions. A common tool used within this data-driven regime is machine learning. So this enables computers to learn and improve from experience or training data without being explicitly programmed. Something that I'd like to emphasize is that when you're training a machine learning model, you're commonly trying to minimize a cost function, which evaluates how well the machine learning model performs for the training data set. And there are many recent applications of machine learning to develop material models. These started up in the early 90s, and they've continued to improve throughout today. Conventionally today, artificial neural networks are the machine learning method of choice to develop material models. These have high accuracy, perform very well with large data sets. There are advanced open source libraries such as TensorFlow, PyTorch. However, they have a fundamental drawback that's prevented their use for engineering applications, which is a lack of interpretability. So what exactly is interpretability? We can think of it as how well a human can understand algorithmic decisions from machine learning. There are a number of reasons why we as engineers seek interpretability. It increases reliability, helps to build trust, and also it informs human decision making. And I'll point you to the figure here on the right. This is sort of a look at how we can interpret machine learning models, and it gives sort of a flow of that. So we capture data from the world, we learn sort of a black box model, and then you can post hoc apply interpretability methods such as decision trees. There are a number of different methods you can use, and these interpretability methods can inform humans. This is a very active area of research, sort of applying post hoc interpretability methods to neural networks, which are black box models. However, these are still often unreliable and misleading, so they're not optimal. So alternatively, this work seeks to use an inherently interpretable machine learning model to develop material models. And this is genetic programming for symbolic regression. So the modification here to the figure on the right, we now just learn from the data, we learn an inherently interpretable model. This is a closed form analytical expression. So common interpretability methods such as feature sensitivities are rarely obtained, and then these can immediately inform humans. So now I'll move into the problem definition and motivation. So this isn't a new idea. GPSR has been used to develop constitutive models. Recently, there was an example of using experimental stress strain data from copper under extreme loading conditions and temperatures to develop a flow stress model within the J2 plasticity framework. This is another advantage of using GPSR. you get analytical expressions that can be implemented into commercial finite element software, things of that nature. Some of the more modern approaches use what's called physics-informed approaches. So you're sort of restricting what models you can get from GPSR so that they abide by known physical laws. But commonly, explicit fitness metrics are used. And so the fitness metric is the cost function for GPSR. This is what you're trying to minimize while you're training it. So taking a different approach, recently published work from Bomarito et al. Developed an implicit fitness metric for developing plasticity models. So this was inspired by seminal works of Schmidt and Lipson from a little over a decade ago, where they showed the benefits of using an implicit fitness metric versus an explicit fitness metric to derive natural laws. So this recently published work from Bomarito et al., they were motivated also by the Prager consistency condition in the development of the fitness metric. So the Prager consistency condition says, under plastic loading, the stress state must remain on the yield surface. And so they were able to successfully reproduce von Mises plasticity from simulated training data. So from this work aims to advance the current state of knowledge by demonstrating the viability of GPSR with that newly formulated fitness metric from Bomarito to develop damage models. We've targeted damage models because they're more applicable for engineers in practice than the von Mises model. And this is just a clear extension of the prior work. So specifically, we are aiming to reproduce a known pressure-dependent plasticity model within the context of ductile failure. So ductile failure is confined within the context of damage models. So here's a problem definition. So our hypothesis is that we are going to be able to reproduce, our hypothesis is that using appropriate fitness metrics, GPSR is an effective tool for engineers to develop interpretable data-driven damage models. And I'd like to point out, we're really focusing on the engineers. We're aiming this work toward engineers. So there are a couple questions we can use to verify this hypothesis. So question one, using that newly developed fitness metric with simulated training data, can GPSR consistently recover a known ductile failure model? Second question sort of targets the engineers. So can we sort of illustrate and explain any dependencies that GPSR has on user-defined variables so that engineers are able to develop accurate interpretable ductile failure models in practice? So before diving into the approach, I'll give an introduction to ductile failure. I'll provide the ductile failure model that we targeted, and then I'll provide an introduction to GPSR. So ductile failure, there are three main stages: nucleation, growth, and coalescence of voids. Here on the right, I've shown void coalescence. You can see there's a crack. This is in initially dense steel. You can also see sort of these smaller voids. Some have grown larger. And the very small ones have nucleated on particle defects or inclusions. A common parameter to describe damage in ductile failure is porosity. So this is a proportion of the volume that consists of voids. Within ductile failure, commonly used models are derived from simplifying assumptions. So these involve voids remaining spherical during the growth, which is not realistic, self-similar void growth, and so on. The most widely known, perhaps, model of ductile failure is the GTM model. This was developed in the late 70s, and this was an extension of the Gerson model. It applied heuristic corrections from unit cell simulations. The Gerson model, it only targets void growth. It has a very simple analytical form. For these reasons, we targeted the Gerson model as a ductile failure model that will attempt to recover with GPSR. So brief introduction of the Gerson model. It targets ductile porous metals. Common applications of this model are additively manufactured metals, where the voids are already pre-existing, often. Also steels, ductile metal alloys, where the voids nucleate, like I said, on inclusions and defects. The Gerson model was the first model to couple plasticity and damage growth. So in the Gerson model, damage is represented as porosity, or F. What I've shown here on the right is Gerson yield surfaces in principal stress space. I've shown it at several porosities. What I'd like to emphasize here is that we know the von Mises is like a cylinder along the hydrostatic axis. The Gerson model closes that off because it is pressure dependent. You can also see the dependency on the damage variable F. As the porosity increases, the yield surface shrinks, so you see a decreased capability to sustain loading. So the Gerson model is defined by its yield function, which I've shown here. This includes the von Mises stress, hydrostatic stress inside of a hyperbolic cosine term. You can see the dependency on porosity here. It's also defined by the porosity evolution equation, which describes how porosity evolves with loading. Okay, and with that, I will now provide an introduction to symbolic regression and then GPSR. So symbolic regression, the goal is to search, well, not the goal, but what you're doing is you're searching the space of mathematical equations to describe a given data set. I'd like to point you to the figure here on the bottom. So this is an example of a function sine of 2x plus y. And then on the figure on the right, I've shown it as a tree structure representation, as well as an operation list, which is how it's commonly stored in the computer. In the operation list, you can see that you have to load each parameter and then apply the mathematical operations to finally get sine of 2x plus y. I'll be speaking throughout this talk about complexity. So the complexity of an equation is the number of steps in its operation list. So for this example, sine of 2x plus y would have a complexity of 6. And then the hyperparameters that define the possible equations to search. So this defines a hypothesis space for symbolic regression. You have mathematical operators. So which operators are available in these functions that are evolving? There's also the stack size. So this sets a limit on equation complexities. So you can't be, so this prevents you from evolving very, very long equations. So now, how do you specifically evolve those equations in symbolic regression? That's where genetic programming comes into play. So you're trying to evolve the equations based on how well they describe the data. This borrows a lot of ideas from natural selection, which makes it interesting. What I'll present on this slide is how offspring equations are created. So sort of the mechanisms to create offspring equations. The first is mutation. So what I've shown here, I've circled a node in this tree structure representation, and you can see that this X mutates to a constant 2. And there are several different types of mutation. You can mutate entire branches or just single nodes. There's also crossover. So showing here on the bottom, the top portion of this tree structure is combined with another tree structure to create an offspring equation. And mutation and crossover rates, these define how often mutation and crossover occur during the evolution process. And these are user-defined hyperparameters that are defined before training. So in GPSR, equations are evolved over generations, again, speaking to the sort of motivation from natural selection. There's another hyperparameter, population size. This defines the total number of equations that are present in the evolutionary process. Common practice is to use parallel computing with GPSR. It is a very computationally expensive process. So you use processors that represent islands. Each island has a certain number of equations. So that's what I've shown here on the bottom right. And then there's a periodic migration between the islands to maintain sort of that genetic diversity. Okay, finally, how do you select parent equations that will reproduce for the next generation? Well, this is based on the evaluation of the fitness metric, which I discussed is the cost function for GPSR. On the left here, I'm showing an explicit fitness metric for an explicit function. very common example is mean squared error, which we're mostly all familiar with. This is used in linear regression, for example. But what I've shown here on the right is instead implicit functions which require implicit fitness metrics. This is because these are not actual definitions of functions. So here, for example, this function, the dependent variable or the independent variable y has two values for each value of x, the dependent variable. So these cannot be evolved using explicit fitness metrics. These instead require implicit fitness metrics. An example of an implicit fitness metric from seminal works of Schmidt and Lipson is the mean logarithmic error of derivatives, which I've shown there. And you can see that you're comparing numerical derivatives of the training data to the automatic derivatives of the candidate equations. If they're very similar, this term goes to 0, log of 1 goes to 0. So this will give you a low fitness value, which equates to a good fitness. So with that introduction, I'll give you a simple example. This example uses Bingo, which is an open source NASA software from GPSR. This is what I'll be using throughout this work. For this example, I generated 100 data points around the unit circle that I've shown there. And I'm using that same implicit fitness metric from the last slide. So here I've defined the hyperparameters, just the common mathematical operators: addition, subtraction, multiplication, division. Stack size of 100, so I'm preventing any equations over length 100 from evolving. Then a population size, I'm using 5 islands for a total of 648 equations. So this example was evolved to a generation 500. What you're left with are hundreds of equations with varying complexity and fitness. So this figure is demonstrating that the blue dots represent candidate equations, each at a variety of fitness and complexities. There are a few key takeaways from this example that I'd like you to see. So first off, I pointed some of the equations along or in this figure. So you can see this small complexity of x, y. Here is the equation of the unit circle: x squared plus y squared equals constant. Here's a more complex example where you have additional terms. You might have noticed that all these equations are equal to an arbitrary constant. This is a remnant of using an implicit fitness metric. Again, you're comparing derivatives, so the constants are, I guess, disregarded with the derivatives. Second, I'd like to point out how the fitness of the target equation, the unit circle, is not 0. It's a finite value. It is close to 0, but not exactly. And this stems from noise from numerical derivatives in the fitness function. So this might be unexpected, using an explicit fitness metric. You might expect, since these were artificially generated, you would get a fitness of 0, but that's not the case here. Finally, I'd like to point out what's known as a Pareto front. So this is typically used in model selection. So you have all these equations, which one do you end up using? Typically, Pareto fronts have sort of an elbow where the fitness it's near the minimum value. After this elbow, you get diminishing returns with fitness. And so you mostly like to restrict your model selection to this elbow area. And you can see for this example, this would provide us with the target equation of this circle. So with that introduction, I'll dive into the approach. Beginning with the generation of training data representative of the Gerson model. And first off, I'll show the numerical integration procedure. So simulated loading is used to generate the training data. I'd like to emphasize that these training data are not just from evaluating the equations, finding the Gerson model. This is able to capture the evolution of variables such as porosity and plastic strain, which I could not do if I was just evaluating the equations. I'll be referring to load cases. So what I mean by that is imposing a total deformation total deformation gradient at an initial porosity over some amount of time, T final. This is assumed to be quasi-static loading, so that's sort of an arbitrary number, final time. This uses a backward Euler method. This has been shown to be a stable algorithm for pressure-dependent models, independent of the curvature of the yield surfaces. So here I'm giving the pseudocode, and I won't go into detail here, but there are a couple things I'd like to point out. First off, you can see here, this n incr, this denotes the number of increments. This is an incremental algorithm. Second off, I'd like to point out sort of this if-then statement here at the bottom. This is distinguishing between elastic data points and plastic data points. So I'll go over here to the figure on the right. After performing a time step, there are two cases. So your stress state could be either inside the yield surface, in which case that's an elastic data point, or the elastic stress predictor could be outside the initial yield surface, in which case you have to perform Newton's method to radially return back to the evolved yield surface. So for this example, I've imposed a final deformation at an initial porosity of 5%, and I've shown that on the figure here. So this is a Gerson yield surface in its stress space, where you have normalized von Mises stress, normalized hydrostatic porosity. And so by doing this, we get just a single trajectory along the surface. I've sort of magnified that image, just really showing that that trajectory consists of data points. But what we would really like are multiple trajectories to fill the parameter space. In our case, this will provide more information about the target surface, bingo. In practice, this is also known to improve generalization of GPSR models. In general, if you get a model in machine learning, you don't want to go too far outside of where the training data are, because this leads to this is, commonly unsafe practices. So how can we systematically select all these final deformations and initial porosities to avoid sparse regions on this surface I'm showing here? And this is where space filling comes into play. So we focus our space filling on the yield surface. This has a more complicated functional form. The domain, I'm restricting it to physically realistic initial porosities, less than 10%. And it's worth noting that in practice, porosities are commonly under, a tenth of a percent, hundredth of a percent, and so on. So this is sort of a high porosity. And the goal for space filling for some number of load cases, we're wanting to populate the Gerson yield surface with an even distribution of initial yield points. And they are initial yield points because space filling is performed prior to running the algorithm and generating the trajectories. So we're really restricted to just space filling on the initial yield points. So for the space filling technique, we evenly increment the initial porosities from 0 to 0.1. Each of these initial porosities defines a contour on the yield surface. And what we would like is for each initial yield point along that contour to be equally likely to be selected as an initial yield point. Once we have that, we can back solve for deformation at yield using, okay. So what I've shown here in the figure is the result of performing this 50 times. I have 50 initial yield points on the surface here. So what we have are a collection of deformations at yield at a number of initial porosities. However, the deformations at yield only provide us with the initial yield points. We would really like to go beyond that to get trajectories along the yield surface. And so we multiply that deformation at yield by a multiplier k. We use k equals 4, which was which was found empirically in this work to perform well, give us good trajectories. So with that space filling technique, I'll now move into the generation of training data sets. So first step, you decide on the number of load cases. You then use your space filling technique to find your final deformations and your initial porosities. You perform the numerical integration algorithm, and what I'm showing here is performed from 1 to NL, so this is repeated NL number of times. Then you want to reduce the number of data points in each load case. So at the moment, we have an anchor number of data points. Sometimes you want to reduce the amount of training data that you give bingo to sort of improve the computational performance. So I'm going to distinguish this with the number of steps, and as you reduce the number of data points in each load case to NS. Then you filter out the elastic data. The Gerson model is a plasticity model, so the elastic data is not representative of the Gerson model, so you filter that out. And then finally, you sort the data for each parameter into columns before you can give it bingo. So for the yield function, we have the input data set shown here. I'm only providing the necessary parameters to recover the yield function. And what I'm showing here in the figure is sort of the result of performing that technique that I showed on the last slide. So you have trajectories that are throughout the yield surface without really any sparse regions. Okay, for the porosity evolution, going back, we have time derivatives present in the porosity evolution equation. However, we're using an incremental algorithm to generate the training data. So this requires us to discretize the above equation. So this equation that I'm showing below is the target equation to recover the porosity evolution. I've shown the input data set for porosity evolution here, as well as the training data on the surface. And something to point out is that there are sparse regions on the surface. The reason for this is that we performed space filling on the yield surface. We didn't consider this in the space filling technique, so we might expect for some sparse regions to exist on the surface. Okay, so now we have our training data. We want to input this into GPSR, showing the relationships. So first, I'll go over the implicit fitness metric that I discussed before, that was recently developed by Balmerito et al. So again, this is implicit regression. You have a function equal to an arbitrary constant. This was formulated within the context of plasticity models. Again, it was motivated with a proper consistency condition. So you have an input data set X, some candidate function from GPSR F, and here on the bottom, I've shown that implicit fitness metric. And so there are a few things to unpack here. First off, you're averaging over all the plastic data points in the data set. On the top here, this is a chain rule for the partial F over T. On the bottom here, you're normalizing by the absolute values, and this was shown to help avoid some of the trivial solutions that are common in implicit regression. So sort of defining what's going on here, we have parameter J in X. So I've shown the training data sets here. So this would specify, for the yield training data set, we would have porosity or normalized von Mises or hydrostatic stresses, things of that nature. And in effect, what this fitness metric is doing is taking average normalized deviation of the derivatives of that. Okay, now I'll move into the training methodology that we used to recover the Gerson model. So we conducted hyperparameter and training data set investigations. These are to sort of shed light on the dependencies of GPSR on the user-defined variables. In these investigations, we're focusing on, again, on the yield function due to its more complex functional form. For training, I'm only providing the necessary mathematical operators. I'm not going beyond that. In practice, where you don't know the underlying functional form, this would be more difficult to decide. So what I'm showing here on the bottom is a flowchart of how we perform this training. So for the hyperparameter investigations, we first looked into mutation, crossover rates, and stack size. Then moved down to the population size. Then the final step was to investigate different training data set sizes. So more specifically, part 1 of the hyperparameter investigation, we're looking at the following values of the hyperparameters. Since GPSR is a stochastic process, we do 20 trials to 50,000 generations at each combination. Because we haven't yet performed the population size or training data set size investigations, we use 10 islands as well as the following data set size. This was recommended by Bommarito et al. When he was developing plasticity models. We then move on to the population size investigation. So again, 20 runs to 50,000 generations. The population size investigation is using the best performing mutation and crossover rates and stack size from the previous investigation. And then finally, we conclude with the training data set size investigation, looking at the following values of the training data sets. And again, this investigation will use the best performing hyperparameters since it's the last. Okay, so here are the results. First off, I'm showing the mutation and crossover rate results. Before I jump into the figures, I'll define normalized fitness. So this refers to the fitness value divided by the fitness of the data to the Gerson yield function. So for the training data set used for this investigation, this was about 10 to the minus 4. But again, this is strongly dependent on the specific data set. So again, dependent on NL and NS. What we see from these figures is that large mutation rates perform best. So we see that the largest mutation rate, 0.75, is noted with the black line. In these figures, it's at the bottom of the curves. So we see that it's reaching better normalized fitness in fewer generations than other combinations. And the reason for this is that the functional form of the yield function requires fork mutation to evolve. So what I'm showing here, say you have like a cosh of some parameter. This requires fork mutation, which takes this parameter, inserts a mathematical operator relating two parameters. And so in this way, you're able to evolve that cosh of 3/2 normalized hydrostatic stress. Another thing to point out, we see larger stack sizes in this zoomed in image. They have a higher tendency to overfit. So this is to be expected. The complexity of the yield function is 11. So going to 60, we do expect to see some overfitting like we did with the unit circle test problem. The takeaway from this slide for using GPSR in practice is that sort of the target equation analytical form ultimately determines the best performing mutation and crossover rates. We don't see much variation in the performance. So these don't seem to have a large effect on the performance of GPSR. But we did see that large mutation rates performed best, so that's what we moved forward with. Moving on to the stack size. What we saw is that smaller stack sizes performed better than larger stack sizes. And I'm showing that through Pareto fronts, which we discussed earlier. Stack size of 15, which is denoted with the red line, has better fitness at smaller complexities than larger stack sizes. This is important from an interpretability standpoint in practice. You're often wanting equations with small complexity and with good fitness. And so stack size of 15 was able to do that best. On the bottom left here, I'm showing the percentage of runs that found the yield function. So we can see using the stack size of 15, we were almost 3 times more likely to recover the yield function than using the larger stack sizes. And so for these reasons, we moved forward with the stack size of 15. Population size, what I'm showing here, we do expect larger populations to perform better. You have more equations, more diversity, but we do see diminishing returns which is an important takeaway for using GPSR in practice. You don't want to be using up all your computational, you don't want computational resources in practice. So we see that 20 islands, once you get to a normalized fitness of 1, where the yield function is at, it pretty much meets up with the 40 islands curve. And so for these reasons, we moved forward with a population size of 20 islands. Okay, moving on to the training data set size study. We saw 100% of the runs recovering the yield function in this study. Larger data set sizes did seem to improve upon finding the yield function. They found it at earlier generations than using smaller data set sizes. But again, there were diminishing returns. So, using tons and tons of data is not necessarily going to give you better performance. So we found a happy medium using 50 load cases with 100 steps each. Okay, finally, I'll show the Gerson model recovery using sort of the optimal hyperparameters training data set size. On the left here, I'm showing the yield function results. This was evolved within an average of 5,700 generations. And by generation 15,000, 100% of the trials had recovered the Gerson yield function. On the right here, I'm showing the cross evolution equation results. It's all much quicker. Average generation to success was 95. We do see significant overfitting though. So by generation 500, the best models have a normalized fitness of 0.1. So about 10 times better than the fitness of this equation. So why might that be? So there are a couple of reasons for this. First off, you're approximating the time derivatives with increments. Remembering back, the actual cross evolution equation had derivatives. Also, the stack size of 15, which I took from the yield function results, that's almost double the complexity of cross evolution equation. And as we've seen, more complex equations are more prone to overfit. So what are the conclusions? We were able to verify that the hypothesis that using appropriate fitness metrics, GPSR is an effective tool for engineers to develop interpretable data-driven damage models. We accomplished this by 1, demonstrating that we could recover the Gerson model, which is a known ductile failure model. And 2, we illustrated and explained the dependencies of GPSR on user-defined variables such as hyperparameters, training data set size. So what does this do? What have we added to the world? This opens the door to generate improved interpretable GPSR produced damage models by relaxing assumptions. As we discussed very early on in the presentation, a lot of those analytical models have assumptions underlying them, and this results in poor accuracy. Getting more into the specifics, we recommend space filling. So this is shown in practice to improve model generalization as well as GPSR efficiency. We also showed that stack size has a considerable effect on obtaining accurate and interpretable models. So in practice, you might want to perform a sensitivity study on stack size or use parsimony pressure techniques. These add a regularization term to the fitness metric, sort of trying to pressure less complex models to evolve. And then finally, from a computational standpoint, there were diminishing returns from using larger population sizes and training data set sizes. So again, in practice, finding a happy medium there would be recommended. As far as future implications go, so assumptions underlying the Gerson model, again, symmetric array of spherical voids. They're assumed to remain spherical throughout the loading, which is known to not be physically realistic. And then also the Gerson model assumes a perfectly plastic von Mises matrix material, which again is not very accurate in practice. So what I've shown here is like a finite element model with pores, and you can adjust the shape of the pores, adjust the distribution of the pores. And this allows you to generate training data with relaxed assumptions to, in the end, get more accurate models with GPSR than the Gerson model can provide. Okay, and then I would like to thank project support from Sandia, as well as support from my advisor, Dr. Hochhalter, as well as my